Hello everyone, welcome to this video. In this video, we need to solve this question which states that prove that the set of all rational numbers of this form 3 raised to power m, 6 raised to power n, where both m and n are integers, this forms a group under multiplication. Now that is very simple. So our given group, let this be represented by the letter capital G. It has elements of this form 3 raised to power m, 6 raised to power n, where both of this m and n, they are integers, right? And we are given the operation as multiplication. So let's first of all discuss about the closure property. So for the closure property, if we take any two elements from this set G, let us take the first element as 3 raised to power m1, 6 raised to power n1, and the second element as 3 raised to power m2, 6 raised to power n2, where these superscripts m1, n1, m2, n2, they are the member of Z, right? So basically they are integers. If that is so, then if we multiply these elements together, because multiplication is the operation that is given to us, so you see by the law of exponent, the powers m1 and m2, they add up together, n1 and plus n2, they add up together. So both of them, because if you add any two integers, it would again be an integer, hence we have this element a member of G again. And this is true for all the elements because we have taken two elements as any arbitrary members of G. Hence closure property is satisfied in this particular case, right? Now let's talk about associative property. Multiplication is associative. If you take any two elements A, B, C, if you multiply A and B first, this would be equal to saying if you multiply B and C first and then with A, they are the same thing. This thing is also applied here because we have the operation of multiplication, hence we can solve any two terms first, correct? So this property is also present here. Let's move on to the third property, which is the existence of identity. So for the existence of identity, let's take some arbitrary element 3 raised to power m, 6 raised to power n from G, right? So basically for this property, we are looking for some x which is a member of G such that when you multiply this x with it, you will get back the same element, right? So can you think of any such element? The answer is this. You have 3 raised to power 0, 6 raised to power 0 as that element x. So that when you multiply the given element 3 raised to power m, 6 raised to power n with this element, you will again get back the same element. Hence, because this is again of the form 3 raised to power something, 6 raised to power something, and that something has to be a integer, in that case, you have found your identity element for this particular set G, correct? Now for the last property, we need to check that whether the inverse of each element exists in G or not. So for that, let's take some arbitrary element from this set G, correct? So that means we are looking for its inverse in G such that when you multiply that element with its inverse, you would get back to the identity element of this particular group, right? So for that, let's see what is this element. So you can very clearly see that this element is nothing but 3 raised to power m, 6 raised to power minus n, 3 raised to power minus m and 6 raised to power minus n. Why? Because if you multiply the given element 3 raised to power m, 6 raised to power n with this element 3 raised to power minus m into 6 raised to power minus n, so you see, because we have the same base, the powers would add up. So m minus m, and here also the bases are same, the powers would add up. So it would be n minus n, right? So it would be 3 raised to power 0 and 6 raised to power 0, right? Which is what? Which is your identity element. So in this case, for any arbitrary element of this kind, 3 raised to power m, 6 raised to power n, you would have its inverse as 3 raised to power minus m and 6 raised to power minus n. Hence, the inverse for each element in G exists, and hence we say, because all the four properties, axioms of a group is satisfied by this set together with the operation of multiplication, hence it forms a group, right? So I hope you understood this question well. That is it for this video. Thank you for watching.